Lesson 2. We're going to actually make these reactions now and then balance them. All right, so this is going to be incredibly important. We are eventually going to talk about amounts. So, and this is going to be a good review lesson, or a good review unit as well, because we're going to talk about N equals little m over big M. We're going to talk about PV equals nRT, gas laws. We're going to talk ideal gas law. We're going to talk about solutions, C equals N over V. So all that stuff is going to be reviewed here. So this is a really good unit here, okay? We're going to be talking about all that as we come through here. We need to know 5 types of reactions. That's what we need to know for this unit here, and basically for this, well, for this year, okay? Some of these you have seen before, perhaps. Maybe some you haven't, or maybe we're going to add on to some, okay? And we're going to include states and all this stuff. Today is incredibly important, so make sure you guys pay attention. If you cannot do these 5 reaction types, and you don't know what the products are, etc., you will not be able to balance them. You will not get the, there's no way, no possible way that you will ever get the right answer, okay? This is important today, very, very important. We're only going to do 3 because that's all the time we're going to have, and I don't want to rush you. So please pay attention. Make sure you ask if there's any questions. Without this, you cannot do the rest of this unit. It's that simple, okay? As I like to say, if you cannot do this, I'll save you the trouble right now. If you have any questions, make sure you guys ask. Here we go. Formation is the first one we're going to look at. Now, some of these are going to be incredibly simple. You're going to be like, this is not hard. Good. That shouldn't be. Just pay attention. Formation is the first one. You guys may have talked about synthesis last year or something like that. Same thing. We just do simple formation. We don't call it synthesis anymore. We call it simple formation. Okay. To make the formation of magnesium oxide. To make, this is not a trick question. To make magnesium oxide, first of all, you have to know that magnesium oxide is an ionic compound, metal and a non-metal. You have to know that magnesium is a 2+. Oxide is a 2-. Remember, don't forget, 0, -1, -2, -3, yes? From Unit 1 stuff. So, 2+, 2-, swap, drop, and reduce. Ionic compounds are strong. They tend to stay together very well. So, most of the time, they're going to be in solid form. In fact, they're always in solid form. We talked about this before. You can go to the back room and check them all out if you want. Now, when you put them into water, it's a little different, okay? But to make this ionic compound, it's in solid form. What do you need? This is not a trick question, okay? What do you need for magnesium oxide? Well, probably a little bit of magnesium and probably a little bit of oxygen. Oh, but oxygen comes in 2s because it's a molecular element, okay? So, we've got a metal and we got our non-metal, but our non-metal, oxygen, comes in 2s. You have to remember for this unit, I have no brighter, clever friends, people stupid, yes? P4S8 and the rest are 2s. And you're going to get plenty of practice with that in the upcoming days. So make sure you know those are called, of course, the molecular elements. You have to know those. I have no brighter, clever friends, people stupid. You have to know those because you use those, okay? Balance, oh, sorry, states. We're going to put on states here because this isn't enough. We should be able to do some states. You look over there on that periodic table. Yours isn't as easy because it's all gray. But over there it tells you. Magnesium, you'll look over there, okay, and it's in gray writing. So in gray writing, that's a solid. If you look over there at oxygen, oxygen is in red writing. O is in red, so that is a gas at room temperature. Okay? Now, last step, we got to balance it. Okay? We got 1 magnesium, 1 magnesium. 2 oxygens, 2 oxygens, which means I have to go back here and put a 2 in front. Done. Okay? Steven? Nope. 2+. Oxide has a 2-. Yep. Okay. Next one. Now, the formation of iron 3 sulfate. Iron 3 sulfate. Well, formation. Let's start with the simple stuff. Forming iron 3 sulfate. Okay. Iron 3, 3+, sulfate's a 2-. We need to swap and drop. Ionic compound. Ionic compounds tend to be quite strong. They stick together very well, so therefore probably a solid. All right? So far, so good. Now, this leads us to the most common mistake when I give you these questions. And I'm going to tell you, you have to do simple formation here. To make iron 3 sulfate, okay, can I go to the back room in the chemistry lab and grab the iron 3 plus ion container and the sulfate ion container and just mix the two together? And the answer is no, right? Where do you get ions from? You get them by placing them into water usually, right? Dissociation, yes? There's no such thing as iron 3 plus ions and sulfate ions in solid form in the back room there, okay? Remember, the ionic compounds are in solid form, yes. But to make that, you need each element by itself, okay? So you need some iron. You will need some sulfur. And you will need some oxygen, okay? You have to put each element by itself. It's simple formation. Simple decomposition will be next. Each element by itself. Because, listen to me closely. I'm at some point going to say, if I gave you 20 grams of sulfur, how much product could be produced? Okay? Well, if I don't write it like this, how am I going to isolate the sulfur? If I put SO4 2 minus, which by the way is impossible, okay? If I put SO4 2 minus, that sulfur is combined with oxygen. How am I going to figure out how much sulfur I need out of sulfate? The answer is it's pretty much impossible, because it is impossible, okay? You need to have each element by itself. So if I ask you how much sulfur, if I give you 20 grams of sulfur, how much product can I make? Okay, each element by itself. Let's balance it. Oh, no, let's put states on. Iron, look over there, it's in gray, solid. Sulfur, look over there. Oxygen, look over there. There you go. Now I know what you're thinking. Geez, do I have to know those? And the answer is, well, at some point in time, yes, you probably should know those. Okay, all the metals are solids. Okay, you kind of know which ones are the gases. There's only really two liquids, bromine and mercury. But nitrogen, oxygen, fluorine, chlorine, and then, of course, the noble gases, and hydrogen, of course, as well. It'll become second nature to you eventually, so it'll be fine, okay? Balancing. Well, I could start with iron right here. So I got iron, and then I got two irons over here. I could do that, and most certainly, that's not a bad place to start if you're not sure. Two irons, right? But the next thing you'll notice is you get to S8. How many sulfurs do I have on the right side? Steve? 3. So remember, this 3 goes to everything inside the brackets only. This 3, this 2 goes with the iron. So 3 sulfurs, yes? Okay? So I got 3 sulfurs on that side, 8 on this side. How am I going to balance that? Lowest common multiple is what that's called, right? Lowest common multiple of 3 and 8 is 24. So you got to make 24 on each side. So I'm going to put a 3 here. 3 times 8 is 24. And 8 times 3 over there is 24 sulfurs. I'm going to tell you right now, if you have sulfur or phosphorus, those tend to be the tricky ones. You want to start with those probably, okay? Because those are always the ones that are going to give you the most trouble, and you're probably going to need the most of to kind of balance it out, okay? So phosphorus and sulfur, probably good ones to start with, a little hint for you, okay? You can start at the left if you want and work your way over, but at some point in time you're going to get to the sulfur one, and you're going to have to readjust the numbers based on that. So sulfur and phosphorus, always good places to start. How many irons do I have now? Or how many Fe's do I have, irons over there? How many are over there on the right side? How much? 16. So let's put 16 here. Right? Look, 8 and 2, 16, yes? How many oxygens do I have way down in there? How much? 96. Yes? 12 here, and another 8 out front. That's 96. Get a calculator. 96. Half of 96, 48. Okay? There you go. Now we're balanced. Okay? Good so far? Not too bad, eh? Decomposition. Hey, if you can do formation, Jack, you can do decomposition. That's a fact. Okay? So, decomposition, opposite. Okay? Decomposition of water. Water is a liquid, by the way. When you break down water, eventually, yes, it turns into, well, actually, the first thing that happens, by the way, is you get water steam. Yes? If you kept on heating that a lot, you would get hydrogen gas and oxygen gas. Sorry. Simple decomposition. Exactly the same as the formation one we did, just opposite, right? We're breaking it apart now. Okay? Don't show me a formation reaction and write the arrow backwards. Okay? I don't know what that means. I've never seen that before. Well, I have. It's marked wrong. That's what it is. I'll save you the trouble. Okay? Don't do that. And if you write it out and then you decide, oh, it's decomposition, I'll just change the arrow. Don't do that. Just write it out again, because I'm just still going to mark it wrong. Okay? It has to be written out going this. We don't do it the other way. Okay? I've never seen that. Let's see. Two hydrogens. Good. Oh, by the way, I got the states from over there. Hydrogen, red. Oxygen, red. Okay? Oxygen, 2 oxygens there, so let's put a 2 there and then a 2 there. We'll be balanced. You're going to get lots of practice on this, and by Wednesday here, end of Wednesday, you're going to be awesome at this. Okay? Sodium oxalate. Decomposition. Sodium oxalate looks like this. It's a polyatomic ion in the top left. Sodium's a 1+, oxalate's a 2-. Swap and drop. 1 comes over down, 2 comes over, yoink, right there. Ionic compound. Solid. Okay? What happens when you heat up some sodium oxalate, when you break it down? You get sodium. Basically, you're looking here, guys, and you're saying, hey, what's the elements that I need to use? What's the elements I'm going to get from that? Well, I'm going to get sodium elements eventually. I'm going to get some oxygen eventually. Oxygen comes in 2s, though. And I'm going to get some carbons eventually. Okay? People want to put down, make up new elements here. You know, look over there, molecular elements. And then you got just monatomic elements, right? Carbon is not one of the molecular elements. It just comes in by carbon. Put the states down. Sodium, solid. Oxygen, gas. Carbon, solid. Okay, and I want to see that for each one of these questions. Balancing, that's where you're going to take into account how many you need of each one, right? That's what balancing does for you. So, 2 sodiums, 2 sodiums. I got 1, 2, 3, 4 O's. Okay, here I got 2 O's, so now I have 4 O's. Okay, 2 carbons on the left side, 2 carbons on the right side. Okay, and you are done. Yes? Good? That's formation and decomp. All you have to remember about formation and decomp, if you hear nothing else coming out of my mouth, each element by itself. Okay? Always. There's no exceptions. Okay? Next. Now, combustion. You guys probably did combustion reactions last year. I'm going to assume that you did. I'm going to assume you did, whether you remember or not, carbons and hydrogens. We're adding on to that this year. Okay? So, there is quite a bit to remember here. First of all, complete combustion reaction involves the burning of a fuel with enough oxygen to produce the most common oxides of the elements, making up the substance that's burned. So, combustion reactions are highly exothermic. You get a lot of heat from them. To predict the products of complete combustion, you must know the composition of the fuel and the most common oxides. All combustion reactions look like this, okay? All of them. So, you get some kind of fuel, whatever it happens to be. We'll talk about what some of those options are, like, well, in a second here. For a combustion reaction to take place, you need fuel and you need oxygen. So when it says combustion, you automatically put that. Okay? Every combustion reaction looks like that. A fuel, and it needs oxygen to burn. Okay? For example, I'll give you some options here. When you put gasoline in your car, right? Gasoline is the fuel. It's got some carbons and hydrogens and some other stuff too. It's even probably got a little bit of oxygen there perhaps as well. Ethanol is something that they put into the fuels as well, right? You've heard of ethanol before at the gas pump probably. Ethanol is a mixture of carbons, hydrogens, and oxygens. This is part of it. When you burn that, okay, you need oxygen. Where do you get the oxygen from? Well, air, when you're driving down the road, goes through the air filter. Yes. If it gets too plugged up, the car doesn't run good because it's not getting enough oxygen to burn, right? So you buy an air filter, it goes through the air filter, it goes into the engine, and the combustion process takes place in the cylinder, right? You need a spark, so you need something for that to happen. If you're talking about a gasoline engine, in a gasoline engine you have a spark, and that ignites the carbon-hydrogen fuel with the oxygen to burn it, combust, right? And that shoves the piston up, and it turns the crankshaft, which is connected to the drive shaft bone. The drive shaft bone's connected to the rear wheel bone, transmission bone. No? Okay. Anyway, in diesel engines, you don't have spark plugs. They use another process. They use compression, basically, or pressure. Okay, and it self-combusts that way. It's a little different. So we'll talk a little bit about that here. Yeah, all right. But you always need oxygen. I just got a smoker for my birthday. I'm going to be smoking some ribs. It's going to be awesome. I'm going to gain about 100 pounds. It's going to be awesome. I got a smoker for my birthday. And the first thing that tells you there is that when you light the charcoal, you can put it in the bottom part, and there's 3 vents on the bottom part, and if you close those vents off, it chokes off the oxygen, and therefore the fuel extinguishes itself. It basically, the charcoal, the briquettes, they extinguish. Okay, there's no more fire. So if you open them all the way, it's going to get smoking hot in there. Okay, because there's lots of oxygen that can get in, and it can combust with those briquettes, those fuel. Okay, and you're going to get a lot of heat out of it. All right, so fuel always needs oxygen. All right, now here's the dealio. If, okay, and you're going to get some products over here, of course. Okay, now, and then we'll show you some examples. I think it'll be okay, but there's a lot of stuff to remember here. Now, if the fuel has carbon in it, okay, so if there's carbon inside that fuel, all right, you will get carbon dioxide produced. So that will be produced, okay? It's carbon. If you're burning carbon, you get carbon dioxide, which is, by the way, what you do when you burn fuel in your car, okay? If you burn hydrogen in the fuel, you get H2O gas produced, okay? Now, those might have been something that you did last year. I'm going to assume that it was. If not, now you know. Sulfur, right? If sulfur's in the fuel, you get sulfur dioxide gas. Where do you know sulfur from? Sulfur doesn't smell good. So, when you're stuck behind the bus, the big cheese wagon, yeah? You know what I'm talking about. And the tailpipe's directed right at you, right? And it stinks, right? That's because diesel fuel has sulfur in it, right? What's the deal with diesel fuel now? It's low sulfur, right? Why is it low sulfur? Because they're trying to take the sulfur out so that you get less sulfur dioxide produced. AKA, when you're sitting behind the school bus, the low sulfur one should have less sulfur dioxide, aka less smell, yeah? But diesel fuel has sulfur in it. That's part of the component, so you're not going to get away from that smell. Okay, now they have other stuff to help with that, et cetera, et cetera. But when you're sitting behind the bus and it stinks, that's what you're smelling, because they're burning sulfur, So you're getting sulfur dioxide produced, and that's what you smell. Nitrogen in the fuel, Shell. Hey, they always, if you watch the commercials for Formula One, et cetera, they always brag about Shell stations have nitrogen-enriched fuel. Yes? Well, nitrogen-enriched fuel will give you nitrogen dioxide. Okay? So, nitrogen gives you nitrogen dioxide. And the last one's a little tricky. If you have a metal as part of your fuel, okay, you will get the most common metal oxide. So I'll give you an example. If you had potassium here, you would get potassium oxide here. K is a 1 plus, O is a 2 minus, right? So that there is only one charge for that, right? So if you had potassium in your fuel, you'll get potassium oxide. Let's say you burn some iron. You get the most common iron oxide. What's the most common one? It's the first one on your periodic table. Iron comes in a 3 plus and a 2 plus. You will get iron 3, because it comes first, so it's the most common, iron 3 oxide. Okay? Which looks like that. Okay? Don't forget about the metal one there. That's the tricky one, and that's the one we usually forget because it's not the one that we do a lot of. Okay? If you had chromium, you'd get the most common, chromium 3 is the most common oxide. Okay? Magnesium, magnesium oxide. Strontium, strontium oxide. Okay? Manganese, you get manganese, whatever the most common charge is, oxide, which I think is, I don't remember, 4, I think. 2? Is it 2 comes first? Okay, manganese 2 oxide. Okay? All right, so let's look at some examples here. Here's what you're going to do. Now, complete combustion of ethane. Ethane looks like this, C2H6, tells you that. Gas. All combustion reactions have to have oxygen. And what are my products? This is the part that's going to be up to you now. Okay? And then, of course, the balancing. Look, here's my fuel. I have carbon here. Look up here. Carbon here. So I get carbon dioxide here. Gas. It's exothermic, guys. It's really hot. So you're going to get gases for most of these. Okay? Look, hydrogen's in my fuel here. H. Doesn't matter how many. H gives me H2O gas. Okay? That's the only two things I have that I'm burning, so those are the only two products I'm going to get. Balancing. Okay? Let's see. 2 carbons, 2 carbons. 6 hydrogens, 6 hydrogens. On the right side, I have 4 oxygens, and 3 more is 7. Oh, only comes in 2s. So, 7 oxygens, right? I can't leave it like that, of course. I don't want you to. I want you to go back and fix it so that we're using lowest whole number coefficients. So, don't forget, I got to go back to the beginning here. This was a 1. I'm going to double it. Double it. Double it. Double it. Okay? And that should be balanced now. Okay? Any questions on that so far? Questions, anyone? Oh. Questions? Okay. Carbon disulfide. Don't forget, you need to know how to name, obviously, write formulas for these, right? That's going to be important. Carbon disulfide looks like that. It's a molecular compound. Combustion, so plus O2. Okay. Now, before we go any further, CS2 is a molecular compound. Okay? If it's ionic, hey, ionic compounds are pretty good. They stay together really well. Okay? Solids. Opposites attract, plus minus, crystal lattice, very good staying together, right? All good review stuff. Hey, CS2 is molecular. Okay. In fact, CS2 is probably what? Linear. AX2, I would think. London forces, size and shape kind of thing. What state is CS2? Well, hard to say. You can't look at that and say, hey, that's going to be a solid, or that's going to be a gas, or whatever. Okay, that's pretty tough. So if I don't tell you for molecular compounds, you can leave it blank, and that's why I've left this one the way it is. Molecular compounds are different because, remember, we're sharing electrons. Where do you get to that special, when do we get to that special melting point or boiling point or whatever? You got to look it up in a book, okay? So that's not as easy. I will tell you, I just want you to leave it blank, but it actually turns out it's a liquid, okay? Which probably most of us wouldn't guess, all right? We're just going to leave it like that, though, okay? So once again, here's my fuel. I got carbon here, so I get carbon dioxide here. Okay. Oh, I got sulfur here, so I get sulfur dioxide here. Okay. Those are the only two things I have in my fuel, so those are the only two products I get. Okay. Done. Balancing. Carbon, carbon, good. S2, two S's there. Oxygens. Let's see. I got 2 here, 2. And that's 4 with the 2 out in front, so that's a total of 6. So over here, 3. Okay, done. All right. And the last one's the doozy here. Save it for last. All right, everyone got that one okay? Yeah? All right, let's give myself some room here. I always run out of room here, so I'm going to have to do this in complete combustion at chromium 3 thiocyanate. Chromium 3 thiocyanate looks like that. Chromium is a 3+. Thiocyanate, you're going to have to look it up. It's a 1-. SCN is a 1-, swap and drop. This is an ionic compound. So, can you tell me the state for this? Absolutely, that's a solid. And you're going to combust it. You're basically going to burn it. Okay? So we're going to put plus O2. Once again, of course, my fuel is right here. And we're going to just start left to right. That's probably the easiest thing to do with these questions. So, look, there's a metal there, okay? So we got to do something with that. That's chromium. You always get the most common metal oxide if there's a metal there. Chromium's a metal, so I'm going to get the most common metal oxide, which happens to be chromium oxide. Well, which chromium is it? It's chromium 3. Look it up on your periodic table. It's the one that comes first. Chromium 3 comes first, so it's chromium 3 oxide. So the right formula for that is 3+, 2-. Swap and drop. Now, that is still an ionic compound. Yes? Metal and oxide, metal, non-metal, so solid. Okay? That's the hard one. The rest, you just have to know. Okay? Sulfur, we know, gives me sulfur dioxide. Carbon, here, gives me carbon dioxide. And nitrogen here gives me NO2 here. Okay? Those are all your products of combustion in this case. So, therefore, balancing. Well, you might say, where am I going to start? Like I said, if you ever get sulfur or phosphorus, you might want to focus on that. So I look here, hey, there's sulfur here, but we're okay with this one because this is not sulfur by itself, so it doesn't come in 8s. This is just 1 here. So that's going to be pretty easy to balance, actually. So I wouldn't worry about that in this particular one. Could you start there? Sure you can. You can start wherever you want, okay? If at all possible, I like to go left to right because it's like reading a book kind of thing, right? So here's chromium. On this side, I got 2 chromiums there, so I'm going to start with the 2 out in front. Okay. On the left side, I have 6. 2 and 3 is 6 sulfurs. I'm going to have 6 sulfurs over here. 6 carbons and 6 nitrogens, right? Remember, this 2 goes to everything behind it, the 3 goes to everything in the brackets, right? So 6 sulfur, 6 carbon, 6 nitrogen. So I go ahead and put all those 6s in there. Good? Yes? Now, let's add up some oxygens here because that's the only thing I got left here. I have 12, 12, 12. That's 36. And 3 more is 39. Yes? 12, 12, and 12, 36, and 3 is 9. Half of 39 is 19 and a half. Once again, is it balanced? Yes. Can I leave it like that? No. Okay. So, easy fix though, go back and double everything. Okay. So, let's go back and do that. I'd say 4, 39. Don't forget to double that one. Okay, there wasn't a number there, so don't forget that one. Double it. Double, double, double. Obviously, you should check if you want to at the end. Okay, I didn't, just to save a little time here, but you can always go back and check if you're not sure. Okay, like for example, you know, if you're concerned about I got 12 sulfurs, 12 carbons, 12 nitrogens. I got the same over there, right? 4 chromiums, 4 chromiums. Oxygens, well, what do you got? 24, and 24 is 48. And another 24 is 72. And then another 6 is 78. And I got 78 there. Okay, so it's all good. You can always double check them, obviously, when you're done. Okay? And that would be a complete combustion of that one there. All right? Now, we're going to stop there today just because I want to give you guys some time to practice some of these. However, I do have one thing to add here. So just listen up for a second. Couple key things for your homework today. When it says it's heated, something's heated up, they're trying to tell you that they're decomposing it. Okay, heating it is like putting it in a hot plate, for example, and basically just cooking it, okay, is what you're doing. You're cooking it. So this is decomposition, really. And make sure you know that that term goes with that. So make sure you know heated implies decomposition, okay, because sometimes they'll just talk about it's heated up or whatever, okay. If it says burned, well, then they're talking about combustion. Okay? Combustion reactions are going to burn stuff. Okay? So that's like a fuel. You're going to burn it. So those are different, obviously, very different. In that case, you would take it, you know, that fuel, and you'd actually put it into the fire, for example, or whatever. You'd be burning it. Okay? Yeah. If it's endothermic, you got to put heat into it then. But no. But if that's different, that's not heating it. That's putting energy into it. I know what you're trying to get at, but when we're talking about heating it, we're not talking about forming it. Okay? It'll say formation. If it's forming, it'll be forming. And if it says decomposition, another term for decomposition is heating it. Okay. All right. Combustion. So those two things you have to know. Also, if you look at question number 8 right now with me here, is one of the ones you're going to do here. It says, I'm actually going to give you the answer for this one here, just because I wanted to show you something here. It talks about when heated, potassium chlorate breaks down into what? Well, what did I tell you guys to do? I said, hey, if you're going to heat this, this is decomposition. And if you're going to do decomposition, I want every element by itself. So I said, well, potassium, chlorine, and oxygen. Right? Each element by itself. That's decomposition. We looked at that earlier today, not too long ago. Okay? In the question, it says this. When heated, potassium chlorate gives you potassium chloride and oxygen. Now, I'm going to tell you right now that I will probably, in most cases, I am not going to say that to you, okay? But the reason we put these on here is because you have to understand, when you heat stuff up, does it all break apart at the same rate? In other words, do they all have the same melting and boiling points and everything else? No. What's going to happen, if you took potassium chlorate and you put it on a hot plate, or basically in a pan in a hot plate, this is what's going to happen, okay? First, because when you look at potassium chlorate, it's potassium and chloride and oxygen, really. Well, potassium and chloride make a very good ionic compound. They're stuck together pretty darn well, or they're going to be stuck together pretty darn well. What's the easiest thing to get rid of out of this compound? Oxygen, because it's a gas, okay? So the first thing that's going to happen when you start to heat this is the gas is going to leave. And it's going to leave you with potassium chloride. But guess what? If you continue to heat this, okay, so now you have this. If you continue to heat that, at some point in time, when you heat it up enough, you will get that, each element by itself. You'll break it down to potassium and chlorine and oxygen, okay? So, is the question wrong? Not really, okay? Is that what I'm going to ask you to do? Probably not, okay? Which one do I want for the homework? I don't care, okay? I'll give you both answers tomorrow if you really want, okay? I don't care. I'd prefer this, actually, because if I say, hey, I'm going to give you 50 grams of potassium chlorate, how many grams of potassium should I get out of that? Well, if I give you this, if you do this equation, it's going to be pretty hard to determine how many grams of that. I mean, there's probably a way you could do that, but it's going to be pretty tough to determine how many grams of potassium you're going to get out of that, because potassium is combined with the chloride, okay? Whereas this is easy. If I give you 50 grams of this, you can tell me how many grams of that you can get. Okay, it's pretty quite simple, actually. We'll look at that. All right? So I'd prefer each element by itself, but if you want to read what they have there and write that out, that's perfectly fine too. Okay, I don't care. But when I ask for a quiz question, I want the top one. Okay, each element by itself, formation, opposite, of course, each element by itself, of course. All right? Good? Let's get you to do some homework here. I'm not going to make you do all of them. Let's do the following. Let's see, 4. We're going to do 5, 6, 8, 9, 10. 4, 5, 6, 8, 9, 10. Okay, let's have those done for tomorrow, because we're going to move on tomorrow, and we're going to do more. Okay.